Welcome back. This is part 3 of Dave Does Calculus from Home. We're talking about section 12.3. Calculus on used to be parametrics. The last two videos were about parametrics. Now it's time for something completely different. Now it's time for calculus on polar functions. It's going to get good. This is part 3. If we're going to do this, we need a quick refresher on some polar functions. One of my favorites is r equals the cosine of theta. Or we can make it a little bigger. Let's have r be 3 times the cosine of theta. This, some of you may remember from pre-calculus. If you make a table of values and start sketching those values, I think you'll find that this is a circle that is tangent to the origin, comes out here in quadrants 1 and 2. We can sort of check this when the cosine, when your angle is 0, cosine of 0 is 1, so you should be out here at 3. Stuff like pi over 4, you're going to get a positive cosine value. You multiply that by 3, you'll be up here. At pi over 2, you get a cosine value of 0. At 3 pi over 4, you should be pointing into negatives, but your cosine is also negative, so it's going to reverse you and it'll push it down here. And at pi, you'll be pointing backwards. The cosine of pi is -1. So you're pointing backwards, but your r is -3, so you're going to end up right back here. And then it just sort of loops around, does this. The circle of diameter 3, that's the point x equals 3, doing loops that way. Passes through the origin. It's not centered at the origin. Touches the origin. So, if this is a standard issue polar function, fairly straightforward, the question then becomes, how do we take derivatives of this function? And the answer is, we pretend it's a parametric function. How are we going to turn this into a parametric function? There's no x's, there's no y's. How is this even going to work? We're going to insert the x's and y's using our favorite polar coordinate equations. X equals r cosine theta, y equals r sine theta. These are our standard issue equations for transforming polar coordinates into x's and y's. So this is exactly what we're going to work with. I know what r is. I'm going to plug this r value into here and into here. That'll give me x equals 3 cosine theta times cosine theta, which is 3 cosine squared theta. This one will give me y equals 3 cosine theta. That's still r. R is always cosine theta. It's very tempting to call this one a sine theta because it's y and it should be sine, but the sine is on the back end. This sine is this sine, that hasn't changed. This r is cosine because that also hasn't changed. So r is 3 cosine theta sine theta, which is just 3 cosine theta sine theta. Not a lot we can do with that one. So now we have x as some function of theta and y as some function of theta. All we have to do is pretend that theta is t, and now we have a parametric function. X and y are both functions of an independent third variable, theta. Easy. So, I'm going to get some derivatives. I'll come here for the derivatives. Start with dy. Y is 3 cosine theta sine theta, which means that the derivative of y needs to involve the product rule. 3 is a coefficient, that can hang out. The derivative of cosine theta sine theta should be first times the derivative of the second, so that's a cosine times a cosine, plus the second is a sine times the derivative of the first. Derivative of cosine is a negative sine. So this will be 3 cosine squared theta minus sine squared theta. Pro tip, for these kinds of problems, you will be taking the derivative of cosine sine a lot. It's going to save you a lot of time if you memorize it as cosine squared minus sine squared. It just makes this easier because you'll see it over and over again. It's a popular sort of expression that comes up a lot. So, I have my dy. Oh, I don't have my dy. I forgot the thing that I tell you always not to forget. There's a d theta on the back end of this. It's like the dt from our other videos. We just toss on a d theta. dx, let's see if I can squeeze the dx down here. X is 3 cosine squared from here. So the derivative of x is a chain rule problem. And this is sort of always going to happen with polar functions. Because you're attaching a cosine to one of them and a sine to the other, it's pretty much always, you're basically always going to get into a situation where the derivative of one uses the product rule and the derivative of the other uses the chain rule. It's, you're going to see these patterns over and over again. So we'll take the derivative of this using the chain rule. 3 blob squareds will turn into 6 blobs. So 6 cosine theta times the derivative of the inside, which is negative sine theta, times the derivative of the inside of that, which is d theta. So my dx is going to be a negative 6 cosine theta sine theta, d theta. So, we have the derivative of y, that was a product rule business. The derivative of x, that was a chain rule business. That's pretty much always going to happen. You've been warned. At this point, I just need to find some space to divide the two. And I think at this point, it's this graph. No, I want to keep the graph because I'm going to talk about the graph later. I think it'll have to be these guys. You've served your purpose, x and y parametric things. It's time to give up your space for something else. I guess I don't need this either. This is important. Put this in your notes. Pause the video. Write this in your notes. Bookmark it or highlight it or do whatever you do to make sure, indicate that notes are important. Because that's important. Okay. dy dx equals 3 cosine squared theta minus sine squared theta over negative 6 cosine theta sine theta. There's a d theta here and here. Those things cancel. I'm already tight on space, so I'm not going to write it. This is my derivative function. I'm not going to do the second derivative of this because that would be excruciating. I didn't have room for the first derivative, and if I tried a second derivative, that would be a quotient rule of a chain rule of a quotient rule with a product rule in the denominator and 2 chain rules in the numerator. That sounds like it would take a lot more whiteboard than I have. So I'm not gonna. It's not super important. We already know how to do second derivatives of these things. What is important is looking at this and interpreting what it means. So I'm going to ask questions like, where is the derivative 0? Where is the slope equals 0? And we can solve that by looking at this. If we want the derivative to be 0, that means we have to set the numerator equal to 0. I'll be done with this stuff for now. If I want the derivative equal to 0, want slope equal to 0. That means set the top equal to 0. If you want a fraction to be 0, you just set the numerator equal to 0. So I'm going to set the numerator equal to 0. That means 3 cosine squared theta minus sine squared theta equals 0. So now I want to solve this for theta so I can figure out which values of theta make the slope equal 0. So I can start by dividing by 3. That'll just get rid of that. And then I can move one of these to the other side. So it'll look like cosine squared theta equals sine squared theta. This equation will give me all of the theta values that make the top of this equal 0. If these two things are equal, then subtracting them gives you 0. And this happens when, you have to be really careful with this. This is super sneaky. We can take the square root of both sides, but we have to remember the plus and minus. You always have this plus or minus business when you take the square root of both sides of an equation. So I'm left with this. The cosine of theta equals positive or negative sine of theta. So we're looking, for those of you who are following along with your unit circles, which should be all of you, we are looking for angles for which the sine and cosine have the same value, but potentially a different sign. Positive and negative sign. And I think if you are following along with your unit circles at home, you will find that this happens when theta is some multiple of 45 degrees. The 45 degree angles are where you have the sine and cosine having the same magnitude, but just various versions of positive and negative. It's all root 2 over 2s at the 45 degree angles. And this is going to be all of the 45 degree angles. So we're going to get a pi over 4, a 3 pi over 4, a 5 pi over 4, and a 7 pi over 4. This is everything between 0 and 2 pi. These are all your 45 degree angles, 45 degree reference angles. It's these guys. And I want to talk about what that looks like over here. Pi over 4 is this angle, which means it's this point. According to my calculus, this point is the first time, I don't need that 3 anymore. This point is the first time that the slope of this function is 0. And that checks out. According to this graph, the slope is very clearly 0 right there. The second place it should happen is at 3 pi over 4. That will be in this direction, but again, that point, the radius was negative, so it was bringing me down here to this point. This is the second point where my slope should be 0. And it is. The third point my slope should be 0 is 5 pi over 4. That's down in the third quadrant, but my radius down there will be negative, so it'll bring me back up into the first quadrant. It hits this point again. Slope is still negative, or slope is still 0 there. And at 7 pi over 4, I'm down here. Slope is still 0. Looking at the graph, it seems pretty clear that this top point and the bottom point are the only times on this function that you get a slope of 0. And according to the calculus, those are the only times you get a slope equals 0. So I think this is particularly beautiful. This is one of those times where if you know what the graph looks like, you should be able to figure this out intuitively. But being able to go through this crazy, weird process to find the derivative and evaluate the derivative and get these numbers to see that you are correct is, to me at least, extremely satisfying. The other kind of thing you can do with this is ask where the slope is undefined. And for that, we want to set the bottom equal to 0. Setting the bottom equal to 0 is actually much easier than setting the top equal to 0 on this one. The bottom is two things being multiplied together, and a 6. I don't care about the 6. If I want the bottom to equal 0, the 6 is relevant, like the 3 was over here. The bottom is effectively a cosine times a sine, and if I want that to be 0, I just need one of them to be 0. It's like a pre-factored polynomial. It's already in two pieces. You just need to set one of them equal to 0. And that is definitely going to happen at 0 makes the sine 0, pi over 2 makes cosine 0, pi makes sine 0, 3 pi over 2 makes the cosine 0, and then I'm back to 2 pi. And those points are here. This is the point at 0 and also at pi. I'm getting a slope of undefined. That means vertical, straight up and down. At pi over 2 and 3 pi over 2, I'm right here. That's the other point where it's vertical. So again, I have something that intuitively is very easy, and if you do it the hard way, you get math that verifies what you thought from the start, and it's very satisfying. That's the end for this video. I got one more video planned. It's going to be a real good one. Don't stop here.